Welcome to Conceptual Physics at Delaware Tech, Chapter 6, Momentum. So in this unit, we're going to talk about momentum, the definition of momentum, and how to calculate it. We'll talk about impulse. Impulse is the change in momentum. So it has the same units, but it is the property that changes momentum of an object that has mass. We'll talk about bouncing, and you might wonder why bouncing. Well, bouncing involves an object going in one direction, having a certain momentum, hitting a surface, and then having a totally different momentum, frequently the exact opposite momentum. We'll talk about conservation of momentum, and this becomes important in any kind of collision event where two objects are striking each other or object is breaking apart into another object, and so the momentum is conserved before and after. If you add up all the momentum before, it's equal to the sum of all the momentum afterwards. And collisions come in two basic flavors: elastic collisions and inelastic collisions. And we'll talk about the similarities and differences between those two. And then finally, a brief word about more complicated collisions. So momentum is a property of moving things, of moving objects that have mass, that have inertia. It's inertia in motion. And the formula for it is P equals mv. P is the symbol we use for momentum. We've already used m a couple times for meter and mass and some other things. So P is the letter symbol abbreviation for momentum. So P equals m times v. Momentum equals mass times velocity. So what's important about this formula? Well, you can see that on the left side, the P is in the numerator. There's no fraction, so it's the numerator. And the m and the v are in the numerator. There's no fraction, so they're both numerator. And that means that momentum is proportional to the mass, and it's also proportional to the velocity or the speed. So if you double the mass, you will double the momentum. You double the speed, you will double the momentum. If you cut the velocity by 1/10 into 1/10, the momentum will go down to 1/10 of the original value. Same thing with the mass. And if you had a conserved amount of momentum and you change the velocity, or excuse me, you change the mass, the velocity would change in accordance. So if you have a constant momentum and you increase mass, the velocity will go down. If you decrease mass, the velocity will go up. Those are inversely proportional to one another. So momentum has direction. It's a vector quantity. We have an object moving in one direction, hits a wall. Its momentum is this way. It bounces off. Now its momentum is in this direction. So there is direction. It is a vector quantity. So here are some examples of momentum and how it relates to mass and speed. A large boulder has much more momentum than a small boulder, small stone, rolling down at the same speed. A fast boulder has more momentum than a slow boulder. So the first sentence just means you increase the mass, you'll increase the momentum. The second sentence means you increase the velocity, you'll increase the momentum. They're both proportional. P is proportional to m, P is proportional to v. At rest, the boulder has no momentum. No matter how gigantic an object is, no matter how much mass it has, if it's not moving, it has zero momentum. Remember, momentum equals mass times velocity. If velocity is zero, m, no matter what m is, m times zero is still zero momentum. A large truck has more momentum than a small truck, even if they're at the same speed. Okay, that's because of bigger m. These are all the same thing, proportionality. So a moving object has A, momentum, B, energy, C, speed, D, all of the above. Well, it's moving, so we know it has speed, and anything with speed has energy, has what we call kinetic energy, and we'll talk more about that in the next unit. And if it has movement and it's an object, that means it has mass, it has matter, so it has mass. If it has mass and it has matter, it has momentum. Interestingly enough, the formula for momentum, mv, requires you to have non-zero values for the mass and a non-zero value for the velocity. Well, velocity speed. So that speed, again, just to remind you, is just velocity without worrying about the direction. But in the next unit, you'll find out that kinetic energy can be calculated with a formula of 1/2 mass times the velocity squared. So what that means is the kinetic energy, the energy due to movement, is dependent on two things, the mass and the velocity. Exactly the two things that momentum requires. So if an object has momentum, that means it had mass, that means it has velocity. If it has both of those, it also has kinetic energy, and therefore it has some type of energy. When the speed or velocity of an object is doubled, its momentum is, well, we've already talked about this. A, remains unchanged in accord with the conservation of momentum. B, doubles. C, quadruples. D, decreases. Well, if you double the velocity, double the speed, you will double the momentum. A says remains unchanged in accord with conservation of momentum, but that is the change in momentum before and after some event. We're not talking about an event where it keeps the same in before and after conditions. We're talking about purposely increasing the momentum of an object by increasing its velocity. So remember, P equals mv. You increase either m or v, that the P will go up, the momentum will go up. So a quick way to test that is, you know, the original momentum before you doubled it is P equals mv. If you double the v, 2v, you'll end up with 2mv, 2 times the original mv. And that's how you know you've doubled it. But you can just remember proportionality and you don't have to go through this. P is proportional to m. P is proportional to v. Do something to m or v, the same thing will happen to P. Now, impulse. Impulse is very similar to momentum. It's the change in momentum. It is the difference between the final momentum and the initial momentum. So it's the change in momentum. It still has units where you're multiplying mass, kilograms, times some speed or velocity, like meters per second. So you might see these unusual units of kilogram meter per second as a unit for momentum. So impulse, being that you're just subtracting two momentum values, it still has the same unit. I will also tell you that in addition to being the difference between the final and the initial momentum, it's also the product of the force that's involved in changing the momentum times the time it takes to do that change. So in formula form, it's this. Impulse is abbreviated as I. It's the final momentum, P sub final, minus the initial momentum, P sub initial. But it is also just equal to the force to cause this change times how much time it takes to make the change. So the force applied over a short period of time, in other words, force times a small t, produces a small change in momentum, a small I, a small impulse. It'll produce a smaller one than the same force times a longer period of time. So you can, in other words, if you put a force on something that's moving, it already has momentum, the longer you put the force on, the more you will change its momentum. That's pretty straightforward, and it's just obvious when you think about it in those terms. If you push with the same force for twice the amount of time, you'll impart twice the impulse and produce twice the change in momentum. In other words, think about the follow-through in sports. If you just hit a tennis ball with a racket and you just go boom like that, you're going to impart a little bit of force on it. But if you spent more time in your connection between the racket and the ball, you'll be able to impart the same force for a longer period of time and therefore change the momentum more of the ball. The ball was originally coming in, and now it's really going to be coming out if you've imparted much more force to it, the same amount of force over a longer period of time. Likewise, if you double the force, if you increase the force, you will also increase the impulse, the change in momentum. That makes sense. If you hit a ball the same way for the same period of time, you hit it lightly with light force, you'll impart a little change in momentum. It'll spring off a little bit. You hit it really hard with hard force, it's going to have a much greater change in its momentum, in its mass times velocity. You're not changing the mass, but you're definitely changing its velocity. So why does I equals ft? Well, you may not be interested in this, but I'm going to go through it anyway in case in case you just like to see where it comes from. Remember, I, the impulse, is the change in momentum. So we designate change as the delta symbol, the Greek letter delta. It just means the change. It means the final version minus the initial version. And so a momentum is just mass times velocity. So it's the final mass times velocity minus the initial mass times velocity. But in most of these impulses problems we're doing, the mass isn't changing. We're just changing the velocity. So impulse is a function of the change in velocity. It's mass times the change in velocity. Well, what is change in velocity? Well, we learned earlier in the semester that from the definition of acceleration is change in velocity over time. If we rearrange that, change in velocity is just acceleration times time. So if we substitute acceleration times time where it says delta v in that equation in number 2, we get an equation that looks like impulse equals mass times acceleration times time. But remember, mass times acceleration, we already learned from Newton's second law, is just force. And now we're left with a simple formula that impulse is just the force that we impart, mass times acceleration, times how much time we impart it. So what I want you to realize here is that impulse can actually take multiple forms. It's the change in momentum, the delta p. It's the final p minus the initial p, the final momentum minus the initial momentum. It is also the final m times v values minus the initial m times v values. And finally, it is equal to the force that it took to make that change in momentum times the time it took to make the change. Now, why is this important? Well, we've already talked about how momentum is proportional to mass, momentum is proportional to velocity, but I want you to look at equation 1 on this page, and you'll see that the impulse is, equation 2, the impulse is also dependent on the change in velocity, And since the change in velocity is dependent on acceleration and time, impulse is also dependent on the acceleration that happened during this event of slowing down or speeding up. It's also dependent on time. If you look back at the final equation, I equals ft, the impulse is proportional to the force. It is proportional to time. Increase the force, you increase the impulse. Increase the time, you increase the impulse. If you have the same impulse, you can increase the force and the time will go down. You increase the time and the force will go down. They are inversely proportional to one another since they're on the same side of the equation multiplied times one another. So let's look at examples. When a force that produces an impulse acts for twice as much time, so we're doubling t, the impulse is A, not changed, B, doubled, C, quadrupled, D, halved. Well, remember, I equals ft. I, impulse, is directly proportional to time. You double the time, you're going to double the impulse. That's what the formula tells us. If we double time, that would be f times 2t, 2 times our original t. That's 2 times the original ft, or double the original impulse. Likewise, if we cut the time in half, we'd have half the impulse. If we cut the force in half, we'd have half the impulse. We double the force, we'd have double the impulse. So this is just saying what I just said. Double the force, we double the impulse. So impulse is what changes momentum. Impulse is the change in momentum, but the act of imparting impulse on something is what changes the momentum of an object. And this is classic for a great many forms of sports. Sports frequently involves changing the momentum of some object, frequently a ball. So applying force for as long as possible, in other words, you're increasing the time of contact, you'll be able to increase its change in momentum, its impulse. The force will vary during contact. So when you're swinging at a golf ball, or you're swinging at a baseball, or you're hitting a tennis ball with a racket, the force that's imparted as it's contacting, it's not exactly equal at every moment in time, but that average force is multiplied by how much time you actually contact the ball or the object you're hitting. So when a golfer swings a club and follows through, the longer the follow through, the more time that force is imparted. It's the same force, but the more force you're imparting, more time you're imparting that force, and therefore the more impulse you're creating, F times T is impulse. The more impulse, the more change in momentum. So if the ball was standing still, you're going to make it fly really fast with a high momentum. If the ball was coming at you, the momentum's this direction, and you hit it, it suddenly has the opposite momentum, so that's adding even double momentum. So that's a big impulse change when you're literally bouncing an object from one direction to another. So when a baseball player hits a ball with the bat and follows through, the ball is coming in with a lot of momentum in one direction, and the baseball player hits it with the bat to impart an enormous impulse to give it not just enough impulse to stop the ball, but to reverse its direction. Crumple zones on cars. These are the parts in the front of the cabin of the car. So you're sitting in the place where there are seats, the cabin of the car. In front of that cabin in the car and behind that cabin in the car are areas where the metal is purposely not that strong, so that when you're hit in a car accident, the car is collapsed at those points, and it takes longer for that collapse to happen, so that most of the force that happens from the collision will be dissipated in those crumple zones, so that the body of the cabin, where your body is, where your legs are, where your head is more protected. So that's why you have crumple zones. A cannonball shot from a cannon with a long barrel will emerge with greater speed because the cannonball receives a greater A, average force, B, impulse, C, both, D, none of the above. Well, first of all, this isn't completely obvious that it's just impulse. I think you should realize it's definitely impulse. The question is it also average force? And the concept that we haven't covered here is that we're making an assumption. We're assuming that the force all along the barrel of the rifle, of the cannon in this case, is imparting the same force the whole way, as long as the ball is in the cannon, the bullet in the gun. It's being given the same force, and the longer the barrel, the more time there is for that force to be imparted, the more impulse can be given to the object, the greater the change in momentum. So greater time in the greater barrel, in the longer barrel of a cannon or a gun, rifle, will provide more impulse, more change in momentum, and therefore more a greater speed, because we're not changing the mass of the object, a greater speed in the opposite direction if it was coming in. But in this case, we're just shooting it out from a zero velocity. So any change in impulse will just give it velocity in one direction out of the barrel. And because we're also giving it velocity and it has mass, we know m times v is momentum, so it's giving it new momentum, and it's also giving it new kinetic energy, because kinetic energy, as we'll learn in the next unit, is 1/2 m times v squared. So they both depend on mass and velocity. If you have both, you have both momentum and velocity. Case 2, decreasing momentum over a longer time. Extend the time during which the momentum is reduced. This softens the blow. So if you've got an object that's moving, it has a certain momentum. It has a certain mass. It has a certain velocity. And if you're going to stop it, that means you're changing its velocity to 0. And that means the amount of momentum you're changing is all of the momentum it used to have. The final momentum will be 0. The old momentum was something. 0 minus something is just the negative something. And the negative just means in a different direction, the opposite direction. So our impulse in this case will be equal to whatever momentum it used to have if we're stopping it dead. If we're either going from movement to dead stop or going from dead stop to movement, the change of momentum is whatever the momentum used to be or whatever the momentum finally was, if one of those two numbers is 0. But one is negative if you're stopping it, and that just means we're reversing direction. So you don't have to worry about that. So catching a ball, you're stopping its momentum completely. Whatever momentum it had, that's the impulse you're imparting to stop it dead. And a soft mitt will do that a lot better than your bare hands. Why? Because a soft mitt requires the ball to come in and go through the mitt before it stops. And that soft padding of the mitt requires the change of momentum to happen over a slightly longer period of time than if it just hit your hard hand. And even more time than if it hit a brick wall. So a mitt is there to soften the blow by increasing the time of the collision. You increase the time, but the same impulse, you're changing the momentum by exactly the same amount. If the I stays the same and the T is greater, the force will go down. And this is a great theory that's used, well, not theory, but it's a great fundamental fact of impulse, that if you have a certain impulse that has to happen because you have a certain mass going at a certain velocity and you need to change it by a certain amount, the impulse is fixed, you can soften the force of that hit by increasing the time of that hit. And that's done in a number of different ways, by braking a car over a longer distance than braking a car over a shorter distance. The force on your body when you're hitting a brick wall, which only takes less than a second of collision time, is going to be a lot worse than if you hit something much softer, like these protective barrels on the highway. Dropping a glass on a fluffy pillow versus dropping it on a steel countertop. If you're dropping the glass, it has a certain velocity before it hits. It's turning its velocity to 0. The impulse is identical whether it hits a hard surface or a soft surface. The only difference is how long it takes to slow it down. And if you take a long time to slow it down, the force is going to be smaller. Big time means low force. Short time, hitting it on a steel countertop, means a high force. And that's why glasses break on a steel top, but they don't break on a pillow. The last example, using swinging arms to catch an egg in an egg toss contest. A lot of you have probably done this. You've been at a carnival or a fair or something, and there's a contest, and somebody throws an egg at you. No, the people that just catch it like this end up with splattered egg on them. The people that catch it with their arms swinging, they take a lot longer to slow that egg down. And as a result, the force on the egg is a lot lower. They've increased T, they've decreased F. And as a result, the force is low enough that the egg is not destroyed in the process. Let's look at this question. A fast-moving truck hitting a haystack versus hitting a cement wall produces vastly different results. I think that's pretty obvious. Which of the following is or are true? Number 1, both experience the same change in momentum. 2, both experience the same impulse. 3, both experience the same force. Which of these combinations are true? Is it all 3 are true? Only number 1 and 2 are true? Only number 3 is true? None of them are true. Give you a second to think about it. Okay. So let's walk through it. The truck is moving at a certain velocity, certain speed, and it has a certain mass in both cases, whether it's hitting the haystack or hitting the wall. And in both cases, it's going to end up with a momentum of 0 because it's going to come to a stop. So they both have exactly the same initial momentum. They both have exactly the same final momentum. Therefore, they both have exactly the same change in momentum. So we know number 1 is true. Impulse is defined as the change of momentum. So by definition, number 1 and number 2 are true. But let's think about the force. When it hits a haystack, it's going to take much, much longer to slow down than if it hits a brick wall. So as a result, only 1 and 2 are actually true. The change of momentum, the impulse, those are the same for both situations. We know the impulse is equal to force times time. But when they hit a haystack takes a lot longer to slow that truck down than a brick wall does. So if they both have the same impulse, That means the ft of one has to equal the ft of the other. But the t of one is much greater than the t of the other. The one with the high ft must have a low force. The one with the low ft must have a high force. And that is a factor of the conservation momentum in this case. Both cases have the same momentum. It's not really a true case of conservation momentum, but they both have the same change in momentum. So they both have the same total product F times T. But one has a higher T, so it has a lower F, and the brick wall has a lower T, so it has a higher F. In other words, if you hit a wall and it takes a very short period of time to stop you, you're going to feel a big force. If it takes you a long time to stop you, you're going to feel a little bit of force. And that's what's going on. And that is why we prefer to hit barriers, protective barriers that are soft, than to hit walls when we're crashing a car. It's also why we have the crumple zones. It's also why we have seat belts that give a little bit. When a seat belt gives, it takes a little longer to slow our body down in the car. When an airbag hits us in the face, yeah, it's hitting us pretty hard, but it's soft. It's a soft bag compared to the dashboard of our car. So our bodies will slow down over a longer period of time in the airbag than they will into the dashboard and the windshield. And therefore, the force on our face and our body will be much less because the time is increased. So be sure to distinguish between momentum, change in momentum, which is impulse, and force, which is force times time is the change in momentum or impulse. When a dish falls, will the change in momentum be less if it lands on a carpet than when it lands on a hard floor? I think by now you're probably getting the idea of the answer, so let's go through. No, both will result in the same change in momentum. Yes, less if it lands on the carpet. No, less if it lands on the hardwood floor. No, it's impossible to tell. Well, I think we know by now they both have the same change in momentum. It happens in a different way over a longer period of time on the carpet than on the hard floor. So the force will be less on the carpet than it is on the floor. But they'll both feel exactly the same change in momentum. They both had the same speed when they hit. They both slowed down to the same zero velocity. So they both had the same change in momentum. It just happened in a different way. So same change in velocity means, and the same mass means they changed the same momentum, the same impulse. If the momentum change is the same, the impulse is the same, the change between MV final and MV initial is the same. So in both cases, it'll just be the negative value of your initial momentum. That's because the final momentum is zero. But the point is they're both the same. So Ft of one must be equal to Ft of the other. They just each have different Fs and Ts. If the T goes up, the F goes down. The longer it takes you to slow down, the less force on whatever it is slowing down. Again, be sure to distinguish between momentum, change of momentum, which is impulse, and the force that happens during that change. So let's continue with that same example. When a truck is out of control, it's better to hit a haystack than a concrete wall. The physics reason is that it's the same impulse either way, whether you hit the haystack or whether you hit the wall. But extending the time of the hitting, increasing the time, T goes up, the force will be reduced for the same impulse, for the same change in momentum, for the same change in velocity of this object. So the same impulse, the same change in momentum can either be with a large force for a short time, which you usually don't want, or a small force for a long time, which is usually a much safer bet. So again, this is why we have all these safety devices in our car. It's to increase the time during a collision, when our bodies hit an airbag, when our bodies hit a seat belt, when the crumpling of the car happens from a collision. All of these things are slowed down by different devices in our car in order to increase the time and decrease the force when we're coming to a dead stop. So when a truck is out of control, it's better to hit a haystack than a brick wall. You have the same m times v, especially if it's a high v, high velocity hitting the wall. You can either hit a wall and have a high v, a high force and a low over a short period of time, high force over a short period of time, or you can have a small force over a long period of time, and that's generally the way to go. So extension of time will reduce the force. Now, another example would be with your own body, especially people that do parkour. In jumping, you bend your knees when your feet make contact with the ground, because extending the time it takes to reduce your momentum as you're jumping down, you're going very fast by the time you hit. You bending your knees will spend more time before you come to a dead stop and reduces the force on you. This is the superhero landing that everybody's seen in a Marvel movie. Somebody jumps from a tall building and they land. You see the superheroes do the little bend. Deadpool even made a joke about it, okay? The bending of the knees is to increase the time and decrease the force on the body. The same thing happens with boxing. A boxer has a choice when they get hit in their body and their face. They can either ride with the punch, where they're actually moving back with a little bit with the punch so that the punch slows down with their face over a longer period of time so they feel less force, or they can just hold their face right into the punch and that fist will stop in a much shorter period of time with a much greater force, and that's what you want to avoid, obviously. But the fist is moving and eventually it will come to a stop. You have two options about how to make that fist stop: over a long period of time with a short force, or over a short period of time with a big force. Now, sometimes you want to do the other. Sometimes you purposely want to create a lot of force when you're changing the momentum of an object, when you're imparting impulse. And martial arts are a classic example of this. In this case, a short period of time is used to deliver a larger force. If a karate expert is splitting a sack of bricks, she's coming down with her hand. Her hand is coming with a certain speed and it's going to stop when it hits the bricks. It can either stop quickly, imparting a large force, or it can stop slowly, imparting a smaller force. So a lot of time, slow time means longer time. Long time, small force. Short time, big force. So martial artists definitely want to do it fast, short time, in order to have a big force. What happens if you do a long time? You end up with a small force and you don't break the bricks, but you end up breaking your hand instead. The time of contact is very short, it's brief, and as a result, the force of the impact is huge. The idea in this case is to maximize the force. Unlike when you're doing a collision and you're trying to protect somebody, now you're trying to impart the most force you can by using the shortest period of time for your contact. Boom, you're in and you're out. And that will have much less effect on your body, but it'll have much greater force on the object you're imparting the momentum to. You're actually changing the momentum of the bricks by doing this. So you want the bricks to have large force in their change of momentum rather than a small force. Bouncing. Bouncing are so impulses are generally greater when an object bounces. Why? Because what is impulse? It's the change in momentum. It's the final momentum minus the initial momentum. Well, if the final momentum is in this direction, but the original momentum was in this direction, and let's say they were the same magnitude, let's say it was 10 kilogram meter per second, and you come in and now you're going minus 10 kilogram meter per second. Well, that means minus 10 kilogram meter per second, that's your final, minus 10 kilogram meter per second, that's your initial. You'll end up with minus, so you'll end up with two minuses, minus 10 and minus 10. That's minus 20 kilogram meter per second. In other words, when you bounce something, you are doubling the change in momentum is double the momentum of either time. So the momentum is gigantic in a bounce. Now, not all bounces are perfect. They might be in an angle, so it's a little bit less. But the fact is, any bouncing activity is a big change in momentum because you're changing direction. And as a result, you can use that bouncing for certain things that I'll show you in another slide here. But the momentum changes from positive to zero and then changes from zero to negative. That's a much bigger change in momentum, a much bigger impulse. So if it's exactly a backwards bounce, your change in momentum is twice the original momentum. What some people refer to as a double impulse. It's not just stopping it, it's making it go the opposite direction of the original. So catching a flower pot from a shelf with your hands, and as soon as you catch it, you throw it back up. So you stopped it initially, and then you immediately throw it back up. That bounce, that's additional impulse. You got the impulse, the change of momentum to come to a stop, and the change of momentum to throw it back up. Double impulse, double change of momentum. It's twice what you would have had if it was just falling one time. So this double impulse occurs whenever anything bounces. It's not always exactly twice, depending on the angle, depending on the speed it comes in and the speed it comes out. But you have this change. You have this first big change in momentum coming from one direction to nothing, and then from nothing to the other direction, sometimes the opposite direction. So there's a wheel called the Pelton wheel. This is a special kind of water wheel. It's not your standard water wheel where the cups just catch the water and the water pushes the wheel around in a circle. This uses a very different concept. It takes advantage of the impulse, the giant impulse of bouncing of water. And I want you to notice that all the cups in this water wheel are shaped like W's. They have double cups in them. So they're double curved cups. Why? Well, if we look at the double curved cup, when water hits it, it doesn't just fill up the cup like it's with a typical water wheel. Instead, it bounces out of the cup. The center of the cup has a little lip sticking out of it. It hits that, it splits the water, and it goes in one cup and goes in the other cup, and they both kind of fly back out of the cup. And as a result, the water doesn't really stay in the cups. It's coming in, it imparts a momentum to the wheel, and then bouncing out, it imparts another momentum to the wheel. So you get a double momentum impulse as a result. And this transfer of the double momentum to the wheel, this double impulse, causes the wheel to spin much faster than you would with a standard water wheel that's really just dependent on how fast the water is moving. So the rotation of the wheel can be used to directly perform work. You can have something attached right to the axis of the wheel, of the shaft of the wheel, the axle in the middle, or you can actually have it turn turbines and make hydroelectric power as a result. So this really is an amazing revolutionary invention by Pelton in 1878, and it's still in use today to create energy from just letting water hit this water wheel. Conservation momentum. So we briefly mentioned this. Let's talk about what it really means. In the absence of an external force, so if you're just looking at a certain thing happening and you're not having anything outside coming in, the momentum of a system will remain unchanged. Now, why do I have a picture of a cannon and a cannonball? If you notice, the cannonball is shooting out to the right, but the cannon is recoiling to the left. That's because if you're starting with zero momentum before you shoot the cannonball, your final momentum has to add up to zero as well. Well, if you're shooting a cannonball out really fast in one direction, you better have something going in the other direction so that its momentum will add up to zero. And what happens is the momentum of the cannonball is exactly equal, but in opposite directions, of the momentum of the cannon, of the big cannon. The little cannonball with low mass ends up with huge velocity coming out, and the cannon with big mass ends up with small velocity going backwards, but m times v of the cannon is equal to m times v of the ball, just in opposite directions. So When a cannon is fired, the force on the cannonball inside the cannon barrel is equal and opposite the force of the cannonball on the cannon. That's Newton's third law. The cannon is acting on the cannonball is acting on the cannon. So the conservation of momentum is a direct consequence of Newton's third law. Some people say Newton's third law is a direct consequence of the conservation of momentum. It depends on how you look at it, but they're really very closely related. If you have one force in one direction and one force in the other, and they're both equal and opposite forces, well, that means the momentum is also going to be equal and opposite. If you're starting with no momentum at all, they have to have equal and opposite momenta coming out. So a cannonball gains positive momentum while the cannon gains an equal amount of momentum in the opposite direction, quote unquote negative momentum. It's just momentum in the opposite direction. It depends on how you want to approach it. And this is referred to as the cannon recoil. You have rifle recoil, you have pistol recoil, same concept. The bigger the weapon, the less recoil, because there's more mass to absorb that momentum. It's mass times velocity is the momentum. And if you have to give it a certain momentum because the bullet or the cannonball has a certain momentum in the other direction, the way to decrease the velocity is to increase the mass. So big cannon is going to have less recoil. A big gun is going to have less recoil. So when there are no external forces present, so in other words, we're just looking at a single system and no external impulse is present. In other words, nothing's affecting our system from outside. No change of momentum is going to happen. Whatever happens within the system, if you add up all the momentum in it before, it will be equal to what all the momentum is afterwards. In other words, the impulse should be zero for a system where you're only looking within the system, no external forces. And this just means that you need an external force to slow things down. In other words, slow your system down or speed it up. So if you want to move something, there has to be an external force. And we saw that before in the unit on Newton's third law as well with the apple-orange cart. You needed to have an external force to move the whole thing. It was the force of friction allowing the whole cart system to move forward. So examples of internal force pairs that cancel each other out. All right, we've already talked about how internal force pairs cancel each other out with Newton's third law. And that is because they're both acting within the same system. They might be different particles. Particle A is imparting a force on particle B, and B is on A. But A and B are both part of the same system, like in the case of a baseball that has many molecules in the baseball. These molecules are moving even when the ball is standing still. But the forces are all within the baseball, so they're all canceling each other out. If you have forces outside of the baseball, that will move the ball. But forces within the ball, they're canceling each other out because they're always in pairs. And they're acting within the ball, on the ball. So they have no effect on the force within. They have no effect on the momentum. So molecular forces within the ball will have no effect on its momentum. And that seems like something you probably never thought would even be possible anyway. So it's easy to accept at this point. And think of it this way. If you're sitting inside a car and you're pushing on a dashboard of the car, you're not really going to move the car. You're internal. You're part of the car at that point. So any forces you put on the car is putting back on you, and they're both within the car. So there is no net force. There's no net change in momentum. There's no impulse as a result. So for all collisions, in the absence of external forces, in other words, nothing outside, momentum is conserved in all kinds of collisions. Two things collide, one thing explodes, two things hit each other and bounce off. All collisions, momentum is conserved. If you add up all the momentum of all the pieces before, m times v of this, and m times v of this, and m times v of that, and you look at everything after, m times v of this, and m times v of that, those sums should be identical. No change in total momentum will occur, either before, during, or after the collision. It's just redistributed. The momentum's redistributed. One piece might have more momentum now and then less momentum later, and this one might have been stopped dead and now is moving fast later. but when you add it all up, all the momenta before equals all the momenta after. It's just redistributed. So in equation form, it means the net m times v before is equal to the net m times v after. Another way to write that is the sum. Remember, this is the Greek letter sigma. It means the sum of all the versions. Sum of all the mv's. So m1 times v1 for particle 1, and m1 times m2 times v2 for particle 2, and everything. You add them all up for all the beginning particles or beginning objects before the collision. Then you look after the collision and say, okay, what's the m of this object and the v of this object? Multiply those together, and you add those all those mv pairs up, and the two have to be equal to one another no matter what kind of collision it is. So here's an example of that with two particles before and after. You have the initial momentum of particle 1, the initial momentum of particle 2. Add them together. It should be the sum of the particle momenta after the collision, the final ones. So there are two basic kinds of collisions: elastic collisions and inelastic collisions. Both have conserved momentum. That doesn't change. Elastic refers to the fact that the colliding objects have certain elasticity. In other words, when they hit, they will return to their own shape. They're not going to get deformed. They're not going to get all banged up. They're not going to release heat from some damage. They will retain their shape. So think pool balls, think rubber balls, think steel balls that we talked about once before when we were talking about elasticity. Actually, I think that's later. Later we'll talk about elasticity. So both momentum and energy are conserved in elastic collisions. So if you add up all the momentum before, it's equal to all the momentum after. If you add up all the energy, which we haven't really studied yet, before, and you look at all the energy after from the kinetic energy due to mass and velocity, 1/2 mv squared. You add all those up. Energy is also the same before and after. That's in an elastic collision. So an example of elastic collisions you can have, if you look down below, there are actually three groups of examples here. So in the example A, you've got 3 different points in time. So you've got the green ball hitting a stationary yellow ball, and then the green ball collides with the yellow ball. This is in just section A here. And then it imparts all its momentum to the yellow ball, and the yellow ball flies off, and the green ball is stopped. So that's a total transfer in momentum. You can have different types of total transfer in momentum where objects bounce. So if you look at B, both the green ball and the yellow ball have momentum in opposite directions. They collide, and they each impart their momentum to the other, so they end up going in the opposite directions again, but now away from each other. So that's another type of total momentum transfer. But you might have partial momentum transfers. Now these are all elastic collisions. Nothing's changing shape. The objects aren't deforming. They're not binding to each other. They still are little balls bouncing off of each other. So in the partial case, you might have one object, the green object, moving faster into a slower yellow ball. That's the top of part C. And as it hits, it imparts some of its momentum to the yellow ball, but not all of it. So the green ball is now slowed down, and the yellow ball has been sped up as a result. So we call that a partial momentum transfer. It's still an elastic collision. All right. No energy is lost because there's no crushing or destroying or attaching of particles, no heating, no additional heat is released. So the energy before of all the particles, the kinetic energy of the particles, is still in the kinetic energy of the particles. It's just redistributed after the collision. We don't lose anything to heat loss from the particles colliding. Now you also have inelastic collisions. Momentum is still conserved, all collisions. But now the energy is not conserved. Why? Because some of the energy is lost somewhere. It's really conserved. It's just gone from the collisions. So these occur when you have a deformation. Two things collide and something gets bent. When two cars crash, one of them is going to get bent up, or both of them are going to get bent up. That's going to be a deformation. So some of the energy went into deforming the car, and some of it even went into heat released from the interaction. As soon as you release some of the heat into doing something else besides bouncing off or transferring momentum, that's an inelastic collision. You've actually used energy to change the shape of the car. That's deformation. If you attach things, they're going to come together. They have different shape as a result. They'll transfer heat when they attach. When they break apart into fragments, when a bomb explodes, that's a type of collision where you're starting with one particle and ending up with a bunch of particles. But there's also a lot of heat released in the process. So fragmentations are inelastic collisions. And anything that obviously generates heat, you can immediately know that it's an inelastic collision. So here's an example of a simple one. Two train cars are colliding with one another and attaching in the process. The momentum is still conserved, but energy is not. So any see an attachment or breaking up in pieces or deformation, that's inelastic. So here's an example of an inelastic collision. A single car moving at 10 meters per second, I think that's about 28 miles an hour, somewhere in that ballpark, collides with and attaches to a second parked car, so it had zero velocity, meaning zero momentum, of the same mass. What is their new speed? Well, we know that the sum of all the momenta before is equal to the sum of all the momenta after. Whether it's an inelastic collision or elastic collision, momentum is conserved. So if we add up all the MVs before and add up all the MVs after, well, before we have the mass of the car, which we'll just call M, and its velocity, 10 meters per second. It's really a speed because we're not talking about direction. And then we have a second car that has the same M, but it has zero velocity, so it has zero momentum. We can just cancel that out. That's what's before. After the collision, the two cars have locked together. So it's one object with double the mass, 2m. So what is the new velocity? That's what we're asking for. What's the final velocity? Well, we know that m times 10 equals 2m times v. Solving for v, we see that v is just m times 10 divided by 2m. Well, the m's cancel, so it doesn't matter what the masses of the cars were. If they were the same masses, the masses will cancel, and it's just the original velocity divided by 2, which in this case is 10 meters per second. So if two objects collide and one's not moving and they have the same mass, the final velocity is going to be half. We've literally taken the single car that's moving, doubled its mass, so we will cut its velocity in half. Because momentum is conserved, P is conserved. If M goes up, V goes down. If M goes down, V goes up. They are inversely related to each other because they're on the same side of the P equals MV equation. That's only if the momentum is conserved. If P stays the same, M and V are inversely proportional. A freight car A is moving towards an identical freight car B. So we know right away they have the same mass, and freight car B is at rest. So B has no momentum. When they collide, both cars couple together. So this is the same situation. Compared with the initial speed of freight car A, the speed of the coupled freight cars is A, the same, B, half, C, twice, D, none of the above. Well, we've already seen that if you double the mass means it would have doubled the momentum, but you can't double the momentum. The only way to keep the same momentum is to have half the velocity in the end. So velocity will go down if you double the mass. Sometimes you have complicated collisions where they're coming in at an angle. They could be inelastic, they could be elastic, but they're at angles. Frequently this will require trigonometry, which we don't expect of you. So if you have two cars at an intersection, they're coming in at a 90-degree angle to one another. They may have the same momentum, they may have different momentum. They may be, but let's take a simple example where the cars have the same mass and the same velocity. They're just going in the same speed, but they're going in different directions, so different velocities. Therefore, when you add the momenta together, remember momentum is a vector. You have to add it vectorally if these are not lined up. You can't do simple addition or subtraction. And you get the same, you do the same thing as we did before with the parallelogram rule. If they're perpendicular, you can just use Pythagorean theorem because it's a rectangle. And you can figure out what the combined resultant momentum is. In this case, if we have same size cars hitting and they have the same speed, but they're hitting at right angles, we're going to end up having the two come together and come off at a 45-degree angle from that intersection as a result of their new combined, vectorially combined momentum. So if you want to find out the value, you just use Pythagorean theorem because they're at right angles to one another. A squared plus B squared will equal the resultant squared. So the resultant is equal to the square root of the squares of the two momenta. It's the same formula we've seen before with velocities and with forces. And this is just showing you how it's done to get that resultant force. And let's look at one more complicated collision, a firecracker exploding. So now the collision is one object becoming many objects breaking apart. But it turns out, even with these crazy inelastic collisions, if you were able to measure all the pieces from the fireworks and all the different directions and velocities of each piece and each mass and add them up vectorally in three-dimensional space, which we would never require you to do, you would find out that they all add up to whatever the momentum was of the firecracker before it exploded. If it was standing still, they'll all end up at zero. If it was falling from the sky, it'll end up pointing down the same as the original object falling down from the sky. It all adds up together because momentum is conserved. Energy won't be conserved. A lot of energy went into heat and probably light in this particular case. But it imparts the momentum to all the pieces, and the total momentum of all the fragments is the same as the unexploded firecracker. No net impulse happens in an explosion. In any collision of any type, as long as there are no external things happening to the collision, impulse is always zero because the momentum is the same before and after. Therefore, the change of momentum is always zero. Zero change of momentum, zero impulse. And with that, we'll stop here.